I mean, I think it's fair to say Garib needs no introduction in this environment, which is one way of me getting out of it. But no, he's been doing these presentations for years. I mean, he's been doing these CC4 study weekends for longer than I've been attending them, so that's quite a long time. And today we'll be telling us all about all the difficulties and annoyances of dealing with metal containing ligands. So please.
Well, thank you. It was another way of saying that I'm too old and time to go. Yes, that's good. Yes, yes, synonyms. I would like to thank organizers for asking me to give this talk, and I will talk about dealing with metal-containing ligands. I think that that is a very complex problem. It turns out to be a very complex problem, and I will just give something that there's some criticism and some ideas that some programs we have developed, and that's a work in progress. The contributors are main contributors are Fei Long. Can you hear me there, by the way? Yes, some. Yes, good. The Fei Long, Kaveh, and Keitara, and Martian. And I would like this talk to be given by them, but since work is not finished, we have not finished it. I didn't want to put them on the fire. So you can shoot me as anytime you want. So plan is like that. Problems in the PDB and CCD and in CCP4 monomer library. And I read a lot of the emails on CCP4 bulletin boards that the monomer library has a problem. And then I get depressed, obviously. So because I feel responsible for that. Then when we looked at the CCD for metal-containing ligands, it was a problem is even bigger. I'll give you some examples. Then in the second part, I will give you some general approach to what are the algorithms we are using, what are the data sources, and how are we going to deal with these problems, and with some current applications. So we started working on monomer library 20 years ago, but in this slide, I wanted to say that in the CCD, there are 40,000 ligands, and out of them, 857 of them are contain metal. And 70 of them are heme-like, and 50 of them are iron-sulphur clusters. And when, I looked at all of them, and checked that are they in the density or not, and you would be surprised at how many wrong structures are there, and how many chemical wrong structures are there. And it is a problem is I think that we have to do urgently something about these metal-containing ligands. And I'll give you some examples. And as I said, that we started working on monomer library with Alexei Evagin. At the moment, he's no longer with us. And it was around 20 years ago, and we made it publicly available. And unfortunately, this monomer library was taken by other groups also. There's some divergence, and we would like to bring the efforts so that we all work together on monomer library on chemistry, because that is probably the most important. Crystallography may go away, cryo-EM may go away, but chemistry will stay, and the biology is a largely interaction of atoms, and we need to work on chemistry more, and to make it more community effort. Keitara put the monomer library on the GitHub, and anybody now can contribute, and there are instructions how can you contribute. And if you have a problem, not you have a problem, if you have a problem with one ligands, and then you can correct them, and then have a pull request and so on. Then everything, then one of us or members will look at your request, and then we will be dealing with it. At the moment, the most active contributors are Keitara, Martin, Robbie, and me to some degree. I would like more people to be involved. If, instead of complaining that we have to do things. Okay, to do things, GitHub gives an extremely good mechanism to work together, and let's use that. So there are three potential problems with dealing any ligands, especially with metal-containing ligands. First one is that chemistry. So we have to make sure that chemistry of the ligand is correct. What I mean by chemistry is bond orders, charges, they must be correct. If they are not correct, and the rest of the programs will derive wrong results. Internal structures. If chemistry is correct, then we can deal with internal structures such as restraints, bonds, angles, planes, and so on. All our efforts are directed to generate internal structures, restraints, and so on. And density of ligands must be consistent with the data. If ligands are not in the density, it means that there's something wrong. Even if ligand is chemical is correct, it is very likely to be wrong, at least in this context, in this protein. Here's an examples of chemistry errors. I always thought that ferrocens are going to be very rare in macromolecules. But it's surprisingly, there are hundreds of ferrocens in the ferrocen-like structures in the PDB. But I'm not sure that all of them are biologically relevant. But, okay, one of the problems in the ferrocens, all ferrocens have problem. Either they have not enough charge, each ring must have -1, or there's no hydrogen, or bond orders are wrong. Any program trying to generate internal structures will get it wrong because the chemistry is wrong. So we have to correct that. Another one, another example, 7He. There's an iron, and if you count the bonds, and then you will get an iron +4, which is not likely. Yes, iron likes to be +2 or +3. And surprisingly, many redundant structures. I'll give some examples in the next slide. For example, this one is cysteine with two metals attached to cysteine. It would be much easier to deal with a cysteine and two metals attached to cysteine. You do not need a new ligand for that. And another redundant or unnecessary ligands. Here's ZXE, ZWO, and these two things are exactly same. There's no difference between them at all. And why there are two of them, I have no idea. Probably somebody knows that. And moreover, there are very similar structures that they are very similar structures. So what we do is that deal with one or two ligands plus links. That would be sufficient to deal with that. Another one is heme attached with something. Or the metal complexes. There are a lot of metal complexes. I think that the number of metal complexes will be reduced in future because most metal complexes were multi-metal complexes were just because of experimental phasing. Now experimental phasing is going down, is a fact. So metal complexes will be less and less, and not density. There are some ligands that are outside densities, and I do not think that we will be dealing with them because even if we get a correct structure, this will not be relevant to biology or to the problem you are dealing with. So, as I said, that there are 400,000 ligands in the CCD. And there are many other problems, and 857 of them have metal inside. 70 of them are heme-like, and I will give you my definition of heme-like structures. And 40-50 of them are iron-sulphur clusters. Probably these structures are most important because they are more biologically relevant than, let's say, ferrocens and other structures. But before going any further, I do a lot of criticism in this talk, but I do not want to blame a user, PDB, or anybody. I think if I would like to blame, I would blame developers because we have not developed good enough tools users to use and to generate good enough ligands, and a PDB to use those tools to validate structures. I think that you should not take it as a criticism, and if any of the structures are yours, and I am to blame. If you want to blame me. Okay. So Now we need to deal with a metal containing ligands. And how do we do that? First, we do a first idea. There are three general ideas. First idea is that let's take a COD and take all metals from COD and then cluster them. And see what we will get. Yes, and from COD, we have Faye has extracted 428,000 metal with surrounding atoms. Then Kave worked on them and at the moment cleaned them up. At the moment, there are 190,000 of metals with their surroundings. And then he classified them. There are a little bit more than 30 coordination clusters. This number will increase, obviously, but not substantially. Number of coordination clusters much smaller. We have already, if you are using CCP4, especially with RefMacat, and then you are using that one of the results from this work that the first two columns and the potassium, the sodium. Potassium, sodium, and calcium, and the metals like that, they are being dealt with now much better than before. We are planning to analyze the rest of the coordination clusters, and that they will come later. So that is one of the sources we are using, that is COD, crystallography open database. It is quite nice, but obviously, as all large databases, this has also the errors. You cannot just take data and use them. You have to verify, validate, and make sure that things are correct. There are so many problems. Somebody asked about glucose-like structures in the COD, and I looked at that, and most of them have high B value. It means that they are higher B value. It means that they are not as good as other parts of the structures. We have to be careful with that. So we derive the data first. First, we try to be generous, and so that all surrounding atoms, even more, are taken, and then we filter them down just to make sure that we do not miss any clusters, any metal oxygen and metal carbon on metal something bonds, and that's been done now. There are 190,000 of them. So first idea is that take from COD all metals with their surroundings. Done. Second idea is that since we are dealing with and not only we, almost all programs are dealing with metal containing ligands, they have problems because metals may have sometimes a lot of bonds and not all bonds make sense and so on. So we had a very simple idea that what we do is that take a metal containing ligand, remove metal, generate restraints, but remember that there are metals, and then we bring back metal and make sure that the hydrogen charges are balanced, and then we have now almost complete dictionary, but without metal. So we add a metal back, and then add some basic distances. Then you use another program that will generate the restraints around the metal based on the coordination analysis. That is done by the program called a metal cord. It is available from GitHub. If metals are not within ligands and they are single metals, then this approach will also work for this one. That is the next one, yes. So first one is that the second idea is that remove metal and generate ligand and bring back metal. And the third idea is that take the PDB examples and look at in the PDB problem with metal containing ligands. One of the problems is that they do not exist outside exist outside the protein. The context is important. Without context, it is very difficult. It could happen that you have one metal with different environment, even within same protein. For a given ligand, let's say that SF4, that's iron-sulphur clusters. Take the best PDB from the PDB, and then find all surrounding atoms and try to make it, and then take this metal with surrounding atoms and look at the database of the metal clusters, and extract and make statistics and bring back, and bond lengths and angles are now can be generated. It has been implemented already in the algorithm in the program by Kaveh. It is available from GitHub. So now we look into the PDB. PDB has a lot of proteins with metal. I think either 40% or 60% of PDB files have metals. Not all of them are biologically relevant. Many of them are artifacts of crystallization. What was surprising that magnesium is not surprising that there are a lot of magnesium in the PDB. But the surprising is that there are not enough sodiums. Probably sodiums are much more difficult to identify than magnesiums, and there are a lot of calcium and zinc and so on. There are a lot of zincs. Too many zincs, I would say, but still there are problems. Yes. So the heme-like structures, and I call the heme-like structures all. If a compound has a 5-membered rings with one nitrogen, and all nitrogens make contact with a metal, then I call it heme-like structures. They are not official name, but that's for me it was easy to call it them like that. So, for example, heme, B12, BCL, R3ZZ, all of them are heme-like structures, and the cobalamin, hemes, and chlorophylls belong to this class. And so, if you think in that way, that makes things a bit easier. So a lot of heme-like structures have problems, and some of the problems are with bond lengths, or for example, here it should be double bonded. Because of that, the whole structure is not good. B12 and B13, they are exactly same with 1 or 2 atom difference, and instead of using B12, and I think we should just somehow educate people that we should use links. We should use several compounds and link between them. Then the number of different ligands we have to deal with will be much less. So one basic validation I did was that to check that what would be the nominal charge on metal, and to my surprise at least, yes, there are a number of cases when charge of nominal charge of metal should be iron should be at least 4, which are wrong. I think iron can be +2 or +3 charge, or zinc with +4 charge. That is not impossible. When a metal is in the protein, it can give 1 or 2 more electrons, so it will have a higher charge. Yeah. Okay. Yes. So that was a SRM, Serohem, and that was highlighted by Dale Tronrod, and then Robbie got in touch with me, and then I compared the PubChem and with the CCD, and they saw that there are substantial differences between them, and then we corrected, and after a few attempts, PDB now has a correction also, and we are planning to send all our corrections to the PDB so that PDB has a correct structures. Well, that's another example where when you have a iron with +4 charge. This is not possible, I think. And the problem with this particular case is that PubChem and the CCD agrees, and both of them +4. So we cannot use a PubChem as a validation source, and as a place where we can go and try to check that our ligand is correct. So iron-sulphur clusters are another class of proteins. I thought that we should have a look and try them and correct them first. And there are some suggestions that the iron-sulfur clusters were in the beginning of life, and they are present in many different proteins, and we have to deal with them properly. We looked at the PDB and saw that there are a lot of ligands with iron and sulfur together, and some of them are more prominent than others. For example, SF4, there are more than 17,000, and FES, there are around 1,500, a bit more than 1,000. So I already mentioned that one of the problems is metal-containing ligands is that you cannot deal with them in abstract form. They have to be in the protein. Context is important. Without context, you cannot generate bond lengths and angles. You have to consider context. For example, in this particular case, that iron must make two more bonds, and then it becomes tetrahedral and becomes happen. Or in another case, this iron makes one more bond, and then it becomes happen. And there are we can now there's a program, the metal cord, and that it can be used to generate files for the restraints for some of the metal containing ligands, but I have not tested all of them. Still work is in progress, and we are working on that. These ideas I described in the beginning, they have been implemented by Faye and Kave, and Faye has written that so-called working name of him team, and very imaginative name, and that is that accepts a zip file and writes output. And then metal cord looks at around the metal and with example PDB. And if you don't give example PDB, then it goes to the PDB and tries to find the best possible. But if you have your PDB file, then you can give your PDB file with -p option also. So apart from problems within the metal and around metal, there are additional problems. For example, in this particular case, in the PDB, there are two links with this cysteine to that SF4. One of the links is correct, another is wrong. And during refinement, obviously, that cysteine goes outside the density, and when you look at the density, there's a positive density. Then after treatment with the programs I mentioned before, and now these things can be dealt with. So if you want to correct these structures, we should not only correct the metal containing ligand restraints, we should also consider that what is possible, what is not possible around metal. So for example, that additional bond between cysteine and sulfur in the is not possible, it is not likely, but sulfur and iron is likely. So if we put correct restraints, then programs will work and produce correct results. So we have implemented several algorithms. They are promising. Still work is work in progress, and but we have put some of the results already on GitHub. And if you want, you can try. And but at the moment, if you try, you have to send feedback so that we improve that. Metal coordination analysis is in the GitHub put by Kave, and monomer library. Again, I'm asking everybody to contribute to monomer library to make sure that we have correct ligands and correct chemistry and correct conclusions. And in future, machine learning may do a better job also. These programs are still under development, and I would like to thank Faye, Kave, Keitara, and Marcin, Alexander, Lucretia, Rob, and Paul. And the main contributors, Faye, Kave, Keitara, Marcin, and Alexander was involved in analysis of some of the bond orders and charges. And I would like to thank you for your attention. And I think I have 4 minutes if people want to ask questions. Yes.
Thank you very much. So yeah, we have plenty of time for questions, and I think Elspeth got in there first. with questions.
She was asking questions even before I started. Yes.
Sorry, I didn't mean. I was just mouthing to myself, and you
Well,
thought I was talking. Yeah.
sounded like okay.
Well, that mouthing was. I was wondering whether your lack of electrons was due to reduction during X-ray analysis of the liver.
Electron density, you mean?
Yeah. Well, no. When you said you were worrying about the lack of about the reduction state of the.
Okay. I call them a nominal charge. Yes? Nominal charge on metals. I do not think these are abstract ligands. They are not. To answer to your question, what we have to do is that we have to get correct structure and then refine and then analyze the environment, and then we can make conclusions that what charge is there. Here, what I'm saying is that for these ligands, it is impossible. Even if you put a lot of radiation, yes, it is. You can obviously, yes, you can. If you put under free electron laser for a few days, and then you will have only. Okay.
But my real question wasn't that at all, actually. It was the ligands that you're talking about. Are you absolutely sure of the identity of the metal that is in the ligand? Because as you know, we've been looking at that with proton-induced X-ray emission.
Yes.
And we found that a third of the metallo enzymes that we've tested, which is now 120, have completely the wrong metals in the PDB.
That is absolutely correct questions, but not for me, not to me, because what we want is that, okay, but our task is that what we want to solve. Yes, you have a chemistry, bonds, atom identities, and generate form restraints within that protein or without. Yes, that is what we want. Yes. Now your question is that to find the real identity of proteins. That is more experimental side. So if we have this ligand, if we have this metal, now is it really this metal in this protein? So for that we need experimental data. Okay, it is only purely computational, no experimental data. Okay, as I said that we are not going to deal with. Oh yes, what was that? Yes. Okay. Yeah. Yes.
Thanks, Garib. I just was wondering. I think it's a very good implementation, but I was wondering how you would deal with delocalizations resulting in partial positive or partial charges when you have these clusters, because they're conjugated systems and you would expect them to be.
Yes. Yeah, that's again an extremely good question, and that is one of the projects we are working on. That what are the charges on particular atoms? Again, not relevant to this particular thing. Here, what we say is that we have one particular molecular structure. Yes, we are not concerned with even resonance. Yes, we have one particular molecular structure. Now derive atom types and derive form bond lengths and bond angles for all atoms involved in this ligand and around. That particular question is extremely good question, but it is not for this one. It is a good question. It is fascinating. Yeah, what are the charges of atoms? And charges of atoms depend on environment. If you change environment, charges change. Yes. For example, if you have that's one of the things why heme-like structures are very popular in biology. Not by researchers, by biology, by evolution. Yes, but the environment changes. That iron changes. It is a charged state, and it also can communicate via P-roles with the surroundings, and that is a fascinating thing. But I think that is one of the things we are working on that. Using electron diffraction or electron microscopy, can we identify charge of atoms? That is interesting thing. But not for this work. For any work, I try. My background is mathematics. Yes, I try to abstract from all other irrelevant things. And abstraction is that chemistry must be correct. Okay, and if chemistry correct in one of the possible states, can we derive accurate structures? Problem is that chemistry in many cases are incorrect. That is what I wanted to highlight. I don't want that question could be answered and should be answered by other experimental techniques. not by just looking at the purely computational part, the bond lengths and angles. Yes. The surroundings are important. That is one of the things we are going to work in next years. Yes. Okay. 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 It is a fascinating thing. I can talk about that a lot. Yes. Okay.
Time for one more question.
Yes.
Hi, Genevieve here from PDBE. And so I just wanted to comment on, you raised HEC as one of the ligands that had
Yes.
this in
Mm.
the charge. was
Yes,
four
HEC
parts
is
of
HEC has more than one problem. Yes, I remember that. Yes, charge is one thing. Yes, but HEC is one of the things that makes a link with the cysteines.
cysteine, yes.
And that is where it has a huge problems to make that link. That has to undergo to so many chemical changes. Bond order should switch from one side to another, and we'll come to all these problems. Let me just finish our work so that I am confident that when we say something, and then I can answer to their queries that are you doing all right? As I said, that at the moment, any questions that comes to see for bulletin board about the monomer library, and it depresses me.
Oh, depressing. Sorry about that.
Let me remove that depression,
that,
and we'll go there. The HEC is one of the problems. Yes,
yeah. Well, I just wanted to highlight that one of the reasons we assign HEC when we're processing entries is because it's covalently bond. And that's the challenge with these metal complexes, is although we can look at the ligands separated from the protein, the definitions have come from those ligands in the context of the protein.
I don't
that's
want
really
to
challenging.
blame anybody. I blame only developers that we have not produced a good enough mechanism to reduce and to simplify things. Yes.
Yeah.
Okay. Why don't you just take the conversation to the bar?
Oh, yes. Okay. Okay. I got inspired by the questions that I was. Now I am less depressed than I was before. Okay. Thank you.
So thank you again, Garib. Thank our other speakers and our runners, Sam and Jake, for running around with microphones. That is a thankless task, and I appreciate it. So, thank you.